Hi everyone. Today we are going to discuss how to solve a frame using the stiffness matrix method, right? So first we need to identify what is meant by uh, what is the behavior of a frame member, right? Okay. So if you have a truss, you have a axial, right? And if you have a beam, you have bending plus shear. A truss member is a combination of these, right? Sorry, frame member, right? So it's a combination of truss action and beam action. So usually, therefore, if you consider a truss like this, right, at each node you can have 3 degrees of freedom. It can go either in this way, either in this way, and the bending, the rotation, theta. Okay. So if we consider a truss member like this, so we usually denote the first displacement u1 on its axial direction, right, and theta 1, u2, v2, and theta 2, and theta is, I'm taking clockwise. Some of the books they may take it as anti-clockwise. Okay, so so we can go ahead and write the stiffness matrix. Okay, if you refer some books, right? So mostly they would use a sign convention like this, right? So you need to be aware. So you want take they don't change this. However, they might take anti-clockwise as positive, right? Doesn't matter if you stick to a particular sign convention, your answers will be always correct, right? And if you're taking theta in this direction, so take moments also positive in that direction, right? Anti-clockwise. So for the example, I will choose this method, even though I'm usually familiar with this method, right? So yeah, so the steps are like this. So this is the stiffness matrix for an element, right? The stiffness matrix will denote it as K, right? So it has all the things nodal forces, right? Local forces, right? So we have shear and bending components, everything, right? So you need to calculate this for each element and then find the displacements using this, right? From this you can find the displacements and then use D, okay, and this is T, use T and transform it. You have to multiply it by T and then if this is K, call this local stiffness matrix, right? So you have to multiply it by K dash. Don't mix up the things. This is K and this is K dash, okay? From this, you can find the local forces. Okay. This is how we do it. So we have the element stiffness matrix, and then you know the external forces and everything, right? You know the external forces, and from that you can find the displacement. From the displacement, you go ahead and find the local forces, right? Okay. So we'll do an example like this. This is quite uh, different, yeah, different from the trusses, because in the trusses, if you remember, I did in previous video, please check on that. When you assemble stiffness matrix, right? Here you have the forces, I mean the reactions, okay, and the external forces. So within these, when you find this displacement using the available equation and plug it back to this equation, you can find the total F matrix. Okay, within this, maybe you know 2 or 3. Others are the reactions that are unknown. So you can find that, and that is your react. Those are your reactions. And finally, when you know the reactions, right, you can resolve it and find the member forces, taking the equilibrium of a node, right? It's quite a bit different in here, right? So we'll do an example. So the example is this. We have the bottle frame. So right. So here's a fixed support. Fixed support. You have a force of 10,000 lbs pounds. This is 10 feet. This is also 10 feet. Okay. And here you have external bending moment, 5,000. Okay. So now I'm going to mark the elements and forces. So I draw the elements. This is element 1. This is element 2. This is element 3. And I taught you how to define the angles, right? So this is first node, second node, third node. So I'll define element 1 from 1 to 2 node. Element 2, this is a node. Okay. Element 2 from 2 to 3. Element 3, I will define from 3 to 4. Okay. So if we define it from 1 to 2, The angle is, take the 1 to 2 direction, right? This is your x-axis, or this one. If you want, you can extend this. So the angle it makes with the positive direction of x, this one is 90, right? For the second member, it is 0, is 90, and for third one, that is in this way. Okay. This way. So we have to extend it, right? It is 270, right? So whether you are making x positive direction or plus, the angle would be like this, right? So from the positive x-axis, right? Check the direction of the element. In this case, it is not the same direction, so you have to extend it. So this is your angle, right? So when you are taking the angle, these two directions are to your same side, right? It's not here you can extend, so it's here. So if your angle is wrong, the entire thing is wrong, right? This is 270, right? So we'll calculate this stiffness matrix, this one, for each element. So here C is cos theta, S is sin theta, right? And E is Young's modulus, A is the area, and I is the second moment of area, right? For the first element is step 1. Right? And theta is 90, so which brings your cos theta is 0 and sin theta is 1, right? So in that method, you have like these things, there's a common term like 12 I over R squared, right? You can separately calculate that. OL over I over L, I over L squared, right? These things you can calculate it separately and plug. So 12 I over L squared is I is given, sorry, in this way. First member E is psi and area is 10 inch squared. I is 200 inch 4. This is for element 1 and element 3. And I is 100 for element 2. Okay. Yeah. Here we go. So we have this is first element. So I is 200. L is 10 feet. So which brings you 120 inch, right? To the power 2. So that will give you 0.167. So if you calculate 6 I over L, that will give you 6. That is around 100 inch cube, right? for inch cube, and E over L, that is PSI, pounds per square inch. Check the units, okay, very carefully. Unit is LB per inch cube. So now you can calculate that matrix K, this one, right? So you know everything. E over L is outside. So this is, I would say, so always take U1 in its axial direction. That's how we have to define it, V1, and I will take theta 1. Okay, anti-clockwise, because most of reference books do it in this way. Okay. And here you have U2, V2, and theta 2 for element 1, right? U1, V1, theta 1, U2, V2, theta 2. It is only to represent the columns and rows only, right? So it's only the K matrix. So the values are, if you take in, yeah, I'll write it in different color. This is 12i over L squared, right? Yeah, 12i over squared, because C is 0, right? S is 1 for element on sine theta cos theta. You only remain with this term, right? Because you can calculate 0.167. This is 0. This is minus 10. So this is 0 minus 10. This is 10, 0, 0, minus 10, minus 10. This is 800. This is 10, 0, 400. This is 0.167, 0, 10. This is 10, 0. This is 800. This part is symmetric. And yeah, you can calculate for element 2 also. Element 2, right? So theta is 0, C is then 1, and S is 0. 12 I over L is, I would only put the value. Is inch squared E over L. Yeah. So K is 25,000. 150,000. So this is element 2 means u2, e2, theta 2, u3, v3, and theta 3. u2, v2, theta 2, 3, v3, theta 3. I have already calculated values, that's why. 0.0835, 5, 0, 6, 100, 0, minus 5, 200, 10, 0, 0, minus 5, 400. Now it's done. Let's right. For element 3, angle is 270, so that means cos theta is 0, sin theta is minus 1, right? So I will on the right k. There is also say 250,000. So this will be u, that was from u3 to v, not 3 to not 4, so that means u3, v3, theta 3, u4, v4, theta 4. Okay, and that would be, I will not write the values, 0.167, right? This is EOL, 0, 10, minus 0.167, 0, 10. This is 10. This is V3, okay, V3 row, 0, 0, minus 10, 0. This is 800, 10, 0. Yes. So now you need to assemble it. Okay. So you have a huge matrix. So which I will write the force matrix. U1, so I will write in capital letters because these are external forces. U1, V1, F1. Right. F2, F3. So you have a long matrix like this, okay, and you know the values of these things. Right. So we have yeah, we have F2, right? Second node and third node. We have the displacements. Other three nodes, other two nodes fixed. Therefore, the displacements are zero. So in here you have a load around 10,000. There's no force in y direction, no moment, no force, but there's a moment. Here's where your sign convention plays the role. So you have taken anti-clockwise positive, so that means 5,000. Okay, so that's a huge part of this matrix, right? Okay, so the scalar is outside, so that would be 250,000, right? You have to assemble it using the way you did it in the cross, right? So you have u1, v1, theta 1, u2, u2, v2, theta 2, u3, u4. This is only to denote the rows. Theta 2, 3, 3, and theta 3, theta 4. Right? Now, for the first element, I can put it here. It is for u1 and v2, u2. right? The values, right? And for the second element, it's from U3 to U3 to V3, right? V3, and then it's from third element is from not 3 to not 4, right? So basically there will be, so if I write in different color, yeah. So you will have an elements like this in this matrix. You will have these 9 elements, right? And there are other, these are the common elements for matrix 1 and matrix 2. So that will be added because matrix 2 also will have element 2 also will have elements in here. So that will be basically added to these elements. So other things are there. Elements. Okay. There will be elements. Scalar is outside. So that will be added with the source here, right? Okay, so that will be added with the first 9 elements of this matrix, right? Basically, if you have, let's say you have from blue matrix, if you have 1 here, from the red matrix, if you have 2 for here, so altogether 1 plus 2 is 3. Okay, you just simply add it, but you should make sure that your scalar is same for each matrix, and you will have other things as this. Yeah, so that means to solve this one, you need only this matrix, others are 0, right? Okay. And you know the displacement at each point is 0, right? That means if you take even these elements, right, it will be multiplied with these zeros, and so that will not be important then. All of these three and final three, right? So then you only need this matrix, because whatever the things here will be multiplied with 0, whatever the things here will be multiplied by 0, right? So you only need this one and these two and this one. To solve it, you can write times. So how 100,000, sorry, 10,000 and the matrix. Okay, and this is 7, 0, 10 minus 7, 0, 0, 10.0, 35, 50 minus 0.35. This is the displacement matrix. U2, 2, theta 2, 3, P3, and theta 3. Okay, so if you take the inverse of this, so you have to use at least Excel. Okay, uh, yeah, because this is a 6 by 6 matrix. You have to find the inverse and multiply with this, right? Yeah. So after finding this one, so some easy steps are there. In 0, you can, yeah, it's better you if you use something like Excel if you want to calculate this one, actually, right? So after calculating this, so if it is, let's say f k and this is d, right? So you have to multiply k inverse by f to calculate d matrix, right? So d will be obtained as this u2 v2 theta 2 u3 v3 theta 3 0.211 inch 0.00148 inch. This is negative, so that means it is in clockwise direction. Radian inch inch. So if we take the second number, so that means in axial direction there will be 0.211. So it is also in this way, and it is a clockwise rotation. Here also it is in this way, but here it is this way, and also clockwise rotation. Okay, so it is like this. Okay, and the moment also clockwise theta will be there, right? And similarly, now you have found the displacements, right? Now you have found the displacement, so you need to multiply that matrix by T, which is this, and with it this matrix, right? So C1 is actually AE over L. C2 is EI over L cube, right? Yes. So I will multiply these things. So F is nodal force vector is K T D displacements. I have the displacements. So that K I have calculated already. So I will not spend time on calculating that. 10, 0, 0, minus 10, 0, 0. This is also symmetric. This is also symmetric, and then you have to multiply it by T and D. Okay, so T is, so for the second element, theta is 0. That means C is 1, S is 0. Set for the second element. For the second element, it is this. Okay. And similarly, the displacement. Now you know for the second element, you know the V2, theta 2, U3, V3, and theta 3. You can calculate, right? And this product should be calculated with this, and you will get two x, 2y, and 2, 3x, 3y, This is for element 2, okay? So this is in LB and LB inch, P, P, P inch, right? So the same thing you can do for element 1 also, because you can calculate K, right? T you know, because theta is 90, and D you know already. U1 is 0, V1 is 0, and theta 1 is 0 because of support. And here you know the values U2, V2, and theta 2. So that means you already know this matrix. You can compute this, you can compute this. So your forces will be F1x, F2x, F1x, F1y, F1, F2x, F2y, and F2. So this has been already calculated. Okay, for this element, it will be minus 317, 499, 76. This is for element 1, okay? Okay. So you might notice that this sign, this is plus, minus, plus. But here you got for minus, sorry, plus, minus, this was minus, right? So what has actually happened? Okay. What actually happened? The problem is the local sign convention, because now if you draw element 1, you will see this minus, so that means it's in this direction. And this is because this is calculated with respect to the element coordinate, right? And this is clockwise. I will not write that value. And at second point, this is 20. This is in other direction, and there's also. So if you draw the second element, right? So you'd had for the second element, you had x around 5, 0, 10, and y is in this direction, and the clockwise movement. Here also clockwise movement. Yeah, x is 21 and y is 70 for this element. So you can see that this is f2y for element 1. it is same, it is in action with f2 x of element 2. So don't mix up these things, right? So if you add these two values at this node, 510 and 290, so you remember that is equal to 10,000, right? Which is the force acting at that joint, right? Okay, so this is how we do it. So hope you understand. So with complex rather than the process and everything, hope you would do a couple of examples and make it to the track. So this is the step that you have to follow, right? Okay, and find the displacement and find using this K, okay, the element nodal forces, local forces, right? See how to simplify, and because if you have, even if you have these elements, there are zeros, so no contribution, right? So whatever is assembled, it will be added if it is common, right? And you finally multiply everything. Once you know t multiply with d and then multiply with this one, you get the displacements, right? So not nodal forces. Okay, find one and you can draw a free body diagram and see what has actually happened. Thank you very much.